Hello, everyone. I'm Bongjoon Hyun from KAIST. Today, I'll be presenting our work on uPIMulator, a flexible and scalable simulation framework for general-purpose processing in memory architectures. This work was done by myself and my colleagues Taehoon Kim and Dongjae Lee and Professor Min-Soo Roo. Let me first explain the motivation of our work. Processing in memory has been explored for decades by computer architects, and with the advent of critical memory-intensive workloads like AI, several commercial PIM technologies have been introduced to the market, ranging from domain-specific PIM architectures to more general-purpose PIM architectures. In this work, we categorize PIM designs based on their level of programmability. Domain-specific PIM designs like Samsung HBM-PIM or SK Hynix AMAX are designed to accelerate matrix multiplication, primarily targeting AI workloads. However, general-purpose PIM designs like UPMEM-PIM are able to accelerate a broad range of PIM applications as they come with their own set of programming languages and fairly sophisticated software stack, enhancing their programmability. So why the emphasis on programmability? Introducing a new computing device to existing computer systems require a non-trivial amount of changes to both hardware and software stack. So having the right level of flexibility and programmability that future-proofs its applicability is critical, which is why this work focuses on the industry's first general-purpose programmable PIM device, UPMEM-PIM. In the rest of this presentation, we seek to uncover UPMEM-PIM's unique characteristics from a computer architect's perspective, which we utilize to find interesting architecture features that we deem will be critical for future PIM architectures to support. To elucidate the unique characteristics of UPMEM-PIM hardware-software architecture, we developed a simulation framework for UPMEM-PIM called uPIMulator. Our simulation framework can use application and library source code written in UPMEM's C language. We use UPMEM's open source compiler called DPU UPMEM DPU-RT Clang, which is based on the LLVM framework. This compiler generates assembly code that is written in UPMEM's own ISA tailored for PIM. The front end of our simulation framework conducts lexical and syntax analysis to construct abstract syntax tree. Then the linker figures out how the application should be linked with the UPMEM libraries. The linker and assembler generates binary files in ones and zeros that the backend can understand. The reason why we implement our custom linker is because UPMEM's linker aborts when the binary exceeds the physical limit of IRAM or WRAM. This can degrade the flexibility of our simulation framework. Moreover, as we will explain later in these presentations, thanks to our linker, we could explore a variety of different research topics because we can map any portion of the PIM kernel to any memory type. The backend models the DPU microarchitecture based on publicly available microarchitecture details released by UPMEM. The backend is an event-driven simulator whose functional correctness is verified over real hardware using the PRIM benchmark suite. Now let us move on to an in-depth analysis and characterization of the UPMEM-PIM architecture using our simulation framework. As mentioned before, we used an open-source PRIM benchmark suite that can run on UPMEM-PIM to evaluate the uPIMulator. The PRIM benchmark suite consists of 16 data-intensive workloads from various application domains, such as linear algebra, graph processing, neural networks, and etc., for which we use different input data sizes for evaluating single DPU and multi-DPU based experiments, as shown in this table. This figure shows the compute and memory read bandwidth utilization of the PRIM benchmark suite. The x-axis is the benchmark names with 1, 4, and 16 threads, and the y-axis on the left is compute utilization, and the y-axis on the right is memory utilization. The red line shows the compute utilization and the blue line shows the memory utilization. As you can see, compute utilization is generally higher than memory utilization, except for binary search and sparse matrix vector multiplications. This means that while PIM-suitable applications are generally memory-bound on conventional hardware like CPUs or GPUs, But when they run on PIM, which has ample memory bandwidth but a slower computing core, the applications start to become more compute bound. The same tendency can be observed in this figure too. The x-axis is the same as before, and the y-axis is the latency breakdown of each DPU state. The issuable state, colored in black, is when the DPU is able to issue and execute an instruction, and all other colors, red, yellow, and blue, are situations where the DPU is not able to issue an instruction due to object memory excesses or structural hazards within the DPU microarchitecture. When we break down DPU's runtime, when executed with a sufficient number of threads, 16 threads in this experiment, we can observe that under many applications, the DPU spends the majority of its execution time executing instructions rather than waiting for the data to come back from DRAM. Again, this means that while PIM-suitable applications are generally memory-bound on conventional hardware like CPUs or GPUs, when they run on the UPMEM-PIM architecture, the applications start to be more compute-bound. We also characterize the PIM benchmark suite's various runtime behavior, but due to timing constraints, we ask you to refer to our paper for more details. We also characterize the PIM benchmark suite under multi-DPU configurations. The x-axis is the benchmark names with 1, 16, and 64 DPUs, and the number of threads per DPU is 16. The left axis shows the latency breakdown of each stage, and the right axis shows the speed up. The corner colored in black shows the portion where the DPUs are running the PIM kernel. All other colors, red, blue, and yellow, are time spent transferring data between CPU to DPU, or DPU to CPU, and DPU to DPU. For data transfers to occur, UPMEM-PIM SDK utilizes AVX vector load store instructions to explicitly move data across two separate CPU memory space and the UPMEM-PIM address space. Because such data transfer latency cannot be overlapped with the PIM kernel execution time across multiple DPUs, the system-wide performance is dominated by data transfers. On the other hand, in NVIDIA GPUs, the programmer can overlap host-to-device or device-to-host data transfers with kernel execution time by using CUDA streams. We believe that a future version of the UPMEM hardware software stack that supports flexible kernel partitioning and task scheduling similar to NVIDIA GPU's CUDA stream can help alleviate such inefficiency, one which we believe can be a good use case of our uPIMulator for architecture exploration. Now that we have covered the in-depth characterization results of the current UPMEM's PIM design, let us move on to our discussion on how we believe future PIM architectures should evolve to become better first-class compute citizens within the overall system. Today's commercial PIM processors employ a simple in-order pipeline without any sophisticated microarchitecture to extract ILP for higher performance. For instance, they do not have superscalers, super pipelinings, or fancy branch predictors. Such a wimpy PIM processor design points leave significant performance left on the table, as conventionally memory-bound workloads now far under the compute-bound regime with PIM. While such a design decision was inevitable because the current generation of PIM processors is fabricated on a density-optimized technology node. Future PIM architectures with more flexibility in area, power, and thermal budget can certainly consider relatively more aggressive, performance-oriented design points with a higher operating frequency and ILP-enhancing microarchitectures. In this case study, we use uPIMulator to see how much performance, can be unlocked in PIM's compute-bound workloads by augmenting UPMEM-PIM's DPU with ILP-enhancing optimizations. In this figure, the leftmost base design points is the vanilla UPMEM-PIM architecture, and we incrementally add more advanced microarchitecture techniques as we move from left to right. Specifically, we incrementally add advanced data forwarding solutions to better handle pipeline hazards, higher register file bandwidth to reduce structure hazards at the register file, a two-way superscalar pipeline, and finally, a 2 times higher DPU core operating frequency. For heavily compute-bound workloads like those highlighted in red in this slide, we can see significant performance improvements with such ILP-enhanced PIM architecture, with modest performance improvements being observed for modestly compute-heavy workloads colored in green. And not surprisingly, for those workloads that are still memory-bound, even under PIM colored blue, the benefits of ILP-enhanced designs are less pronounced. Overall, many data-intensive workloads exhibit compute-bound behavior when executed with PIM, and we believe enhancing PIM's computational throughput will likely become much more important in future PIM designs. Another feature we believe will be critical in future PIM architectures is the support for multi-tenancy. Multi-tenancy is one of the most important features for processors to provide for cloud deployment, as it helps better saturate the processor's compute and memory resources, reducing its total cost of ownership. Unfortunately, our case studies reveals that current commercial PIM chips, whether it be UPMEM-PIM or domain-specific PIMs, are not able to meet the requirement of multi-tenancy, not just from a hardware-software perspective, but also from its programming models perspective. Due to timing constraints, let us focus our attention on two important conditions to be met for multi-tenancy. First, collocated workloads should be securely executed without interfering with each other. To enable such a security feature, one of the fundamental architectural support that is needed is isolating the memory address space of collocating applications using MMU's address translation capability. Practically all commercial PIM systems are designed without an MMU, as an UPMEM-PIM uses physical addressing. Therefore, collocating multiple workloads with the address space isolation is fundamentally impossible in MMU-less PIM architectures. In this case study, we add a hardware MMU to UPMEM-PIM using our uPIMulator and study its performance implications. Our MMU model employs a single page table worker, and the page size of which is 4 kilobytes, and is backed with a single level 16-entry fully associative TLB. We utilize such a mechanism to translate all DRAM accesses from its virtual to physical address and measure its performance regression. Overall, an MMU additive PIM experiences an average performance loss of 0.8% with a maximum of 14.1% by adding address translation to DPU's memory accesses. Such low performance overhead is mainly attributed to UPMEM's scratchpad-centric memory model, where data transfer across DRAM and scratchpad are orchestrated in coarse-grained chunks whose size is in the order of several kilobytes over DMA instructions, exhibiting high spatial locality and thus achieving high TLB hit rates. Overall, our analysis reveals that enhancing security guarantees of PIM through proper MMU support, which is a necessary condition to enable multi-tenancy, is practical as it incurs reasonably low performance overhead. However, even UPMEM-PIM does have an MMU, there is another significant problem that needs to be resolved. Since UPMEM-PIM only supports scratchpads without a cache, when two PIM applications are to be collocated and they each require more scratchpad memory than the physical limit, the system will crash. Consequently, collocating both of these workloads require a non-trivial amount of changes to both collocated PIM programs to make sure the aggregate scratchpad usage fits within the physical limit, arguably an unacceptable requirement to enforce to end-user application developers. In other words, collocated workloads must not be aware of the fact that they are concurrently executing. Supporting transparency to collocated applications therefore cannot be honored under UPMEM-PIM's current scratchpad-centric programming model. Therefore, we believe that to properly support multi-tenant execution in PIM, not only on MMU, but more importantly, a user-transparent cache architecture support is needed. Putting things together, our previous case study motivates the need for future PIM to also employ on-demand caches rather than single-handedly relying on scratchpads to guarantee transparency to multi-tenant workloads while still providing the ability to reap data locality benefits. That is, PIM programs running on top of an on-demand cache will be able to leverage data locality in an opportunistic manner while not having to change the program itself. To this end, in this final case study, we implement an on-demand caches and compare its efficiency versus the original scratchpad-based PIM execution by modifying our linker and backend simulator. The modified linker maps binary files only to the DRAM bank, and the modified backend simulator is augmented with an instruction and data cache in between the processing core and the DRAM bank, capturing locality in an opportunistic manner. In this figure, we compare the performance of UPMEM-PIM using only scratchpad colored in red and UPMEM-PIM using only caches colored in blue. The y-axis shows the speed up when the performance of the scratchpad-centric design is normalized to 1. Our results show that some benchmarks are faster with caches, while other benchmarks are faster with scratchpads, which is expected. But our intention with this case study is to highlight the fact that the on-demand caches, when used properly, can still perform competitively for PIM-based designs as well, allowing collocated applications to not worry about right-sizing its scratchpad usage, thereby guaranteeing transparency to end-user PIM programmers who seek multi-tenant deployment of PIM applications. Lastly, we open-sourced our simulation framework uPIMulator on GitHub, which can be accessed through the GitHub link at the bottom. So here are the 3 key takeaways from our work. In this paper, for the first time, we developed a cycle-level simulator targeting the industry's first general-purpose PIM architecture, conducting a detailed characterization of real PIM benchmarks. Using this simulator, we conduct several case studies that uncover interesting research direction for future PIM architectures, for instance, supporting ILP, enhancing microarchitectures, multi-tenancy, and on-demand caches. Our hope with this work is that our open source uPIMulator will help broaden the scope of the research that PIM architects can explore. Thank you for listening to our presentation, and I will be happy to answer any questions.